Here's a nice mechanics problem that I found in a pretty old textbook, but I think it's very suitable for students who are trying to understand Newton's second law. So this is related to forces, accelerations, and there's also an element of constrained motion which is taking place in this problem, and we're going to try to get our head around that as well. So as usual, if you know something similar that you're struggling with, or if there's anything in particular that you'd like me to go through, let me know down in the comments. So in this problem we have a system of pulleys and we have three masses. So we have a fixed pulley called P1, and we have a mobile pulley, we'll call it, which is P2. And then one of the masses, namely M1, is unknown, and the other two masses are, one is 200 grams and the other one is 100 grams. And we're gonna label them as well, because I don't usually like to work with numbers. I'll just use symbols. So this is gonna be M2 and this is gonna be M3 because M1 is taken. And other than that, I think we can start drawing the free body diagrams of each object. Now, what the question is asking is, the question wants us to find the value of M1, given that the 100 grams mass, which is the one we labeled M3, is at rest, which is interesting. So essentially, as you set up the system, and once you let it go, all the masses would normally accelerate, but in this case, mass M1 would accelerate, up or down, we don't know yet. Mass 2 would accelerate, up or down, we don't know yet. But M3 would be at rest, which is interesting because as you look at the system evolving over time, assuming the strings are long enough, of course, the 100 gram mass, the M3, will stay in like the same place, and everything else, like no, M1 and M2 would move, but M3, with respect to a ground observer, would be in the same spot. And understanding what that means, I think, is the key to solve this this problem. So let's actually try to draw some free body diagrams first. So I'm going to start with M1, which is a bit strange because we don't know much about this at all. Actually, I changed my mind. I think I want to do M3 first. I think that's probably the easiest and the most sensible thing to do. So I'm going to do M3. So M3 is experiencing two forces. So there is our, there's the weight, which is M3G, and then there's the tension, like this. And what I would normally write at this point is I would write that tension minus M3G is equal to M3A3, which is obviously correct. Now, in this case, we know that this object, this third mass, is at rest, right? Which means clearly that A3 is equal to 0. So we can say that the tension minus M3G is equal to 0. So the tension in this string is M3G. Okay, good. Now, this tension is not acting only on this object, it's also acting on this object. Now, in reality, this is not really the case, but it is the case here because we're making an assumption that it's like an unwritten assumption, right? So that is that the pulleys and the strings are massless. The assumption is pretty good for the strings. For the pulleys, it depends, but we're making the assumptions, both assumptions nonetheless. So in any case, we found the tension. So what I'll do now is I will actually do the same free body diagram, but for M2. So let's see what happens to M2. So this is my M2, and I'm just going to draw M2G and tension. Now this tension, remember, this is the same tension as the one acting on M3, which we found is equal to this. So instead of ending up with a massive linear system in the end. I'm gonna try to substitute some unknowns as I go along, because you know, if it's easier, I'll just do it. So this tension is going to be equal to M3G, and I'm considering that upwards is positive, right? Normally I also consider that the right direction is positive, but I don't really care about anything going to the right in this case, right? Because all the objects are either going up or down, so in the positive direction or in the negative direction. Anyway, so what we can do here is I'm going to assume, without loss of generality, that the acceleration of M2 is going upwards. Okay, if I'm wrong, then the final answer for A2 will be negative, which we won't even get A2 in the end, because we'll do some substitutions and we'll get rid of it, but we'll assume it's in the positive direction. So we can say that T minus M2G is equal to M2A2. Yeah, that's plain and simple Newton's second law. So we can then say that tension, or instead of tension, the weight of 3, so M3G minus M2G is equal to M2A2. Okay, I don't think there's anything more we can do at this point, other than substitute in the values of M2 and M3. So yeah, technically we can find A2 at this point, but I'm just going to leave the equation like this for now. So I'm going to call this equation 1. Well, this would be equation 1, but yeah, we'll skip that. Now I'm going to do something else. Namely, I'm going to look at the free body diagram of pulley number 2. So pulley number 2 looks like this, and it's being acted upon by 3 forces, right? So we have a tension here, which, let's use yellow because, you know, we like to be consistent with things. So this is tension, which is M3G. This is also tension, which is also M3G. And then there is tension acting from the string above, which let's call this T prime for now. Now, we don't know what T prime is yet, but we can actually use a trick to find T prime. And the trick we're going to use is based on the fact that the pulleys are massless. So this pulley will have an acceleration. I mean, there's no reason to assume it won't have an acceleration. So let's write it as AP2, which might be up, might be down, we don't know yet. But it has an acceleration, so what we can then say is that, well, if we apply Newton's second law to this pulley, we get that T prime minus, so there's 2 M3Gs, is equal to the mass of the pulley times the acceleration of the pulley. But we know this is 0, right? Not because the acceleration is 0, but because the mass is 0. So this assumption here helps us write the fact that the tension acting on the upper string is actually 2 times the tension acting in the lower string. So what this means technically is that T prime is 2 M3G. So the tension in the upper string, as I said, is 2 times the tension in the lower string. So with this in mind, we can draw the free body diagram on M1, on the unknown mass, right? So let's see what that is. So we have M1G, which is that's going down. So this is like that. So we have M1G, we have the tension, so this tension is going to be equal to 2 M3G, right? And this object is going to accelerate maybe up, maybe down, we don't know yet, but I'm just going to make it, I'm going to draw it upwards for now. And I'm going to write 2 M3G minus M1G is equal to M1A1. Okay, so there's one thing, and the other thing is that, well, is this equation. So we have M3G minus M2G equals m to a2. Okay, this is how far Newton's second law brought us. So it wasn't able to bring us to the end of the problem because unfortunately we have too many unknowns. So we have two equations, right? This doesn't count as an equation because I've used it, and I've used this one too, so it doesn't count either. So we have two equations and we have three unknowns. So let's try to see what the unknowns are. I think we have m1, which is here and here, and the acceleration. So we have a1 and we have a2. That's it. So we have too many unknowns, unfortunately. So from this point on, we can't use any more of Newton's second law to figure out the answer to the problem, where, remember, the answer should be what's the value of m1. So we have to make use of something else. And that something else is related to constrained motion. So I'm going to say something that's going to be obvious, which is the mass of the, not the mass, the length of the strings are constant. And this is going to be, surprisingly, the key to figuring out the rest of the question. So let's talk about the string, the lower string. So if I kind of draw it a bit more clearly, like this. So we have, this is pulley P2, right? And there's mass M3 here, and there's mass M2 here, and yeah, that's it. And you know, this is obviously, the masses are moving. Well, M3 is not moving, but yeah, in general, they are moving. And no matter how they move, and this is key, so no matter how those masses move, the length of the string is going to be constant, obviously. It's not an elastic string, right? Yeah, the question doesn't say, but it's not an elastic string in this case. And as I said, this is going to be the key to figuring out the answer to the question. So here's how this works. We're going to take a datum point on the ground, because remember, my vertical direction is positive. So I'm going to write y as my vertical direction, and I'm going to put a plus here. So what I'll say is I'm going to write the obvious thing, which is the length of the string, L2. I'll use L1 for the first pulley. So I'll say L2 is constant. And now people may wonder, like, how can this help us figure out what's happening? Well, it does, surprisingly enough, because we can express the length of the string in terms of the coordinates of the objects. So here's what I say. This length has 3 parts. Well, technically it's 3 parts, but I'll just use 2 parts, and you'll see why in a second. So this string is made of this bit plus this bit. And technically there's this bit as well, but I'm gonna ignore it. I'm gonna say that's very small, and it will be irrelevant, as you'll see. So I'm just gonna say that the length of the string is gonna be made of the left side, which I'm gonna call it D1, and this here, which is D2. Okay, so I'm gonna say that L2 is equal to D1 plus D2. So L2 is equal to, so I want D1 and D2 in terms of coordinates. So here's how this works. I'm gonna say that this point here, right? So this coordinate, this is the y of the pulley. And this right here, this is the y of mass 3. So this is y3, right? And in the same way, this is the y of M2. So this is y2. Right, so D1 therefore is y of pulley 2 minus y3, right? So it's literally this distance from here to here. And then plus And D2 is going to be similar, so it's going to be the y of the pulley minus y2, like this. Okay, so we can say that L2 is equal to 2yp2 minus y2 minus y3. And the neat thing about this is that we can differentiate this with respect to time. Those are all continuous functions and everything. So we can differentiate this with respect to time, and I'm going to do it twice. And when I do that, because L2 is constant, it vanishes. So this is going to give us that 0 is equal to 2, the acceleration of pulley 2, minus the acceleration of the second object, minus the acceleration of the third object, like this. Okay. So this gives us a relationship between the accelerations of objects 2, 3, and the pulley they're attached to. And this is, you know, for this kind of situation, this is always true. Now, we know that A3 is 0, right? Because we're told that the third object is at rest. So we can say that 2AP2 minus A2 is equal to 0. So I'm just going to convert this into A2 is equal to 2 times the acceleration of the second pulley. Okay, so we're going to use this, but we don't have anything to do with it right now because there's no pulley acceleration in this linear system. So I'll do the same thing, but for the first pulley. So the first pulley, which is fixed, so this is going to be important in a bit, is going to look like this. So this is pulley 1, and this is attached on one hand to pulley number 2, and this is attached to M1. And I have my datum point somewhere down. And again, I'm using the fact that the length of the string is constant. And my y direction is going up, like this, in the positive direction. And then what I have is, well, I can express the y's of each component. So this is yp2, this is y1, and the final y, this is yp1, I guess. So we can write the length as, you know, the left hand side, which is this bit plus this bit. So the bit on the left is yp1 minus yp2 plus the bit on the right, which is yp1 minus y1. So we end up with a similar expression actually. So 2yp1 minus y1 minus yp2. Now when I differentiate twice this time around, what's going to happen is that two things will go away. So I'm going to get a 0 here because, again, the length of the string is constant, but this yp1 is also constant because the pulley is fixed, remember, right? So the top pulley is not going up or down, it's just staying there. It has the same constant y value always. So this is 0 minus a1 minus ap2. Or we can write that ap2 is equal to minus a1. So we use this, and we use this, which was A2, make sure I write the correct thing. So A2 is equal to 2AP2. Okay, so we can eliminate AP2 because we don't really want to care about it. And we write it as A2 is equal to 2 multiplied. Now AP2 is minus A1, so we get that A2 is minus 2A1, which is nice. So we found a relationship between the two accelerations. So this was our missing puzzle piece, if you want to call it this way. So this was the last equation that we were missing that helped us figure out, that will help us figure out the answer to the question. So let's write the linear system again. So let me actually do this. And I'll put this here. And on top of that, I'm gonna say that A2 is equal to minus 2A1. 3 equations, 3 unknowns. So now we can actually solve it, and I'll do that by first substituting for A2. So I'll say 2m3g minus m1g is equal to m1 a1. So I'll leave a1 as it is, and then we'll say m3g minus m2g is equal to m2 multiplied by minus 2a1. Okay. Now we have 2 equations, 2 unknowns. We don't know m1. m1 is our goal, right? And a1 is the other thing we don't know. So what I'll do here is I'll eliminate a1 by dividing the 2 equations by each other. But actually before that, I think what I want to do is I'll keep the top one the same and the bottom one, because I don't really like this minus here, so I'm gonna multiply this equation by minus 1 first. So this is m2g minus m3g is equal to 2m2a1. Okay, now it's looking good. We can divide, and we're gonna get, so I'll do the bottom minus the top. So I have m2 minus m3 over 2m3 minus m1, which is 2m2 over m1. Obviously the g's cancel, the a1s cancel, which is nice. This is what we wanted. And now we can find m1, we just have to cross multiply. So we have m1 m2 minus m1 m3 is equal to 4 m2 m3 minus 2 m1 m2. Okay, right. So what we can do now is move some things around. So I'll put this on the other side. So we have 3 m1 m2 minus m1 m3 equals to 4 m2 m3. So here we have m1 times, so I'm going to factorize 3m2 minus m3, which is equal to 4m2 m3. So if you want the final answer in like symbolic form, which is in my opinion the best way to write the final answer in physics, this is what it turns out to be. Yeah, so now we just plug the numbers in. 4 times m2 m3, so 4, and m2 was 200 and m3 was 100, so it's 200 times 100. This is 3 times 200, so it's 600 minus 100. So this is going to give us that m1 is 8 with 4 zeros. Divided by 500, which, you know, we can do this, and we get 160 grams, and that's it. So I think a simulation would be really nice to do at this point somehow, to visualize what's happening. So if we make this mass 160 grams, that mass m3 is going to be at rest, so it's going to be it's not going to be moving with respect to someone from an inertial frame of reference. So yeah, it's just going to stay in the same place essentially, and this is how you do this. So there's a mix of Newton's second law, which we applied 3 times, 4 times if you include the second pulley, and there are some elements of constrained motion as well, which I think are quite interesting and useful. But in any case, that's the end of the question.